And thank you everyone for coming. It's a pleasure to have the opportunity to tell you about this series. It's really a series of projects, most of them with my collaborator, Ruben Veresen, who's also a postdoc at Harvard, but with a number of other people as well. And the archive links you can see here. Can you see my cursor? It's all good if I highlight stuff?
Yep.
Okay, great. So I'm going to tell you a little bit about each of these projects. So what I'm going to do is review a bit of SPTs, and this talk will mostly be in 1+1 dimension, where things are very concrete, especially when we get to the gapless part. We'll be using the machinery of CFT. And so we'll review a bit about the theory of those SPTs, and then I'll get into the gapless stuff. And the main example of what I'll call a gapless SPT will have to do with edge modes at a transition from an SPT phase to a symmetry breaking phase. And I'll go on to talk about more complicated examples, some that have edge modes, some that don't. And the main theme of the talk is going to be to try to figure out a bulk boundary correspondence, when you can detect edge modes from bulk observables. And I'll end with a little extra on emergent anomalies and what we're calling intrinsically gapless SPTs. So to review for you, there's roughly two main families of topological phases that are well collected into families. There's topological order, which the paradigmatic example is the fractional quantum Hall effect. These systems have a ground state degeneracy that depends on the topology of space. So for instance, in the fractional quantum Hall effect, if space it's a 2+1 dimensional system. If space is a sphere, there's typically a unique ground state, but if space is a torus, there are several ground states. And those ground states are identified with so-called anyons, which are particle-like excitations, or in higher dimensions, they can be string-like or even surface-like, that have non-trivial braiding statistics. And the braiding statistics is encoded in a topological quantum field theory, or a TQFT. And in fact, you can say that under the RG, so these are gapped systems, that the system flows to a TQFT in the infrared. And these systems are stable gapped phases without any symmetries. Any kind of perturbation, you can't suddenly change the nature of the anyons without closing the gap. On the other hand, we have SPT order, or symmetry protected topological order. So the main example here, or the most famous, is the topological insulator. These systems don't have any ground state degeneracy, and they don't have any anyons either. So they really look quite trivial in the bulk. It looks like a trivial gapped phase. But nonetheless, if you study them on a system with a boundary, you find interesting physics going on at the boundary. For example, there could be spontaneous symmetry breaking. The predicting symmetry could be spontaneously broken at the boundary, or we could have some gapless modes. And the way to understand this is that the infrared limit of these systems, if we couple to a background gauge field for this global symmetry, that integrating out the bulk gives us a topological term for the gauge field, and the topological term is not gauge invariant on a manifold with boundary. And so we can say that the boundary has an anomaly, and that's why it has to be non-trivial. So these systems are stable as long as the symmetry is unbroken. Okay, so if you can break the symmetry, they really are just a trivial phase. So not included in these two families are a bunch of interesting things, such as fractons that Nadia has actually done a bunch of work on recently. And there's also topological semi-metals like Dirac and Weil semi-metals. There are fractionalized Fermi liquids that mix characteristics of Fermi liquids with deconfined gauge theories, like discrete gauge theories, C2 gauge theory. And then there are other gapless phases. And for us, these are going to be gapless SPTs. So this is a bit of a oxymoron. Most people would say that part of the definition of an SPT is that it's a gapped system, but nonetheless, these will be SPT-like. There'll be some gapless system that has an unbroken symmetry, such that on any if you study it with a boundary, so long as you don't explicitly break the symmetry at the boundary, there has to be some non-trivial thing going on there. It's either some zero energy modes at the boundary or maybe some gapless modes. And we'd like to understand these systems. So these first 2 points are the definition. Now, some facts. So far, the ones we know can all be understood in terms of some kind of topological term. So these are roughly like a CFT with some non-trivial discrete torsion. And the edge modes are stable so long as the bulk system doesn't change. So we're not really going to be concerned with whether these are phases per se. Typically, they will have symmetric relevant operators, but we'll just say that we just won't touch those. We'll just be considering, we could consider a critical point, for instance, as a gapless SPT. We're allowed to fine tune so long as we're not breaking the global symmetry, we'll still have edge modes. But typically these systems can be perturbed into a nearby gapped phase where the edge modes are gone, or where the edge modes become a bulk degeneracy.
Yes? Excuse me for interrupting. Unless you stipulate that the bulk theory is infrared free, I don't know what it means to say that the boundary is non-trivial.
So there's not a preferred boundary condition in these systems, but what I would like to say is that every boundary condition is somehow non-trivial. I'm not saying that there's like a unique boundary condition.
But I don't know what non-trivial means if the bulk theory is infrared free. If the bulk theory is a free field theory at long distances, then I understand what you'd mean to say that the boundary is, well, there still are potential questions, but then you might be able to say what you mean by the boundary being non-trivial. But
yeah, so thanks for the question. I'll get into it. In 1+1 dimension, which is my main focus, it'll always be some kind of degeneracy on an interval, which you can see because in finite size splitting, there will be bulk states of energy 1/L, and then the edge states, the degeneracy will be states that whose energy goes to 0 faster than 1/L. So they could be exponentially small in the length, or they could be algebraic with some power higher than 1. In higher dimensions, it's some kind of similar thing where we have to study a finite system and look at the scaling of the energies. And we could see bulk scaling of the size of the bulk or scaling of the size of the boundary, and look for things that we can identify with bulk degrees of freedom. So for instance, in a 2+1 dimensional system, we could really see modes that are gapless along the boundary, right? There could be local operators that have algebraic boundary correlations, but exponentially decaying bulk correlations. So it's true. It's very finagly, but yes.
I guess you exclude trivial cases where it's a gapless phase tensor product with the standard SPT phase.
Yeah, so I'll talk about that.
So that clearly satisfies your definition, but I hope this is not. You have more interesting examples.
We have more interesting examples, but I think you'll be surprised that that example is more interesting than you expect. Okay. So let me review 1+1 DSPTs for you. So the main feature of a gapped system, or that we can use in a gapped system with unbroken symmetry, is called symmetry fractionalization. So we're gonna study symmetries which are on-site, meaning that the unitary operators for these symmetries are tensor products of local unitaries for a Hilbert space associated with each site. And if you have something like this, it's natural to define the action of the symmetry in some region by just taking the product of operators which are contained in that region. And if we do that to the ground state, the effect is actually the same as just applying a local operator near the ends of these regions, where this local operator will be exponentially localized near the end, given by the correlation length. So we can write an equation like this, where VL and VR are these operators drawn in orange. So
is this an axiom or a corollary or something?
This follows from having a gapped symmetric ground state. You can prove it using MPS states, for instance, or some clever stuff with Schmidt decomposition.
Do you need an so you don't need an MPS ground state?
Well, I'm not sure you need it, but every gapped system in one dimension does have an MPS ground state, or at least can be approximated well.
Yeah, but usually you prove things under some set of assumptions.
Yeah, so just given a symmetric gapped ground state is enough. So we say that the symmetry is fractionalized because we've taken one operator and split it into two. Now, let's say that G is abelian. We get an invariant of this phase by thinking about the charge of these endpoint operators. And this defines, you could think of this as a homomorphism. For every group element, we get a pair of endpoint operators. And for every other group element, we get the charge of that endpoint operator under that group element. So we have this map, G times G to U1. And for abelian groups, this homomorphism actually determines the phase. And it's an invariant. We must go through a phase transition in the bulk, or we have to explicitly break the symmetry to change it. And the bulk boundary correspondence for these systems tells us that if these endpoint operators have non-trivial charges, that we have to have something going on at the boundary. And in this case, what's going to happen is that we're going to have some projective symmetry action at the edge, where these charges are going to show up in the commutators of the symmetry operators. So let me show you just a pictorial proof of this fact, because it's cute. I think it's interesting. So suppose that we apply some symmetry G and then some symmetry H, but we're only going to do it in a region. The region's going to contain the boundary, but the other endpoints are going to be in the bulk, and they're going to be well separated from each other. So here we're applying first the one on the bottom and then the one on the top. That's my convention for this drawing. So time is going up, if you like. And now the bottom one, since we're applying it to the ground state, we can use symmetry fractionalization. Oh, sorry. The first step, we start like this with the little one on top and the big one on the bottom. The first step is to use the fact that these are just products of local symmetry operators, and every local operator forms a representation of the group. So these two operators are going to commute with each other. Then we use symmetry fractionalization to split the small one of these into the endpoint operator and the symmetry operator at the boundary. So there's going to be some effective symmetry operator at the boundary that can maybe change the ground state that we have at the edge. We expect to have some degeneracy. And when we commute these past each other, we get two contributions. One contribution is from the charge of the endpoint operator, and the other contribution is from the commutator of the symmetry at the boundary. Once we've done this, we see that we're really applying the top two operators to the ground state again, right? Because we could factor the bottom operator into, again, a boundary symmetry operator and an endpoint operator over here. And as long as these are well separated, we can think of this pair of operators as acting essentially in the ground state. And so we can replace it with the symmetry operator again. So this is back where we started, but it's only back where we started if we solve this equation, which is that the commutator of the boundary symmetry operators is the charge of the endpoint. So this tells us that what was an abelian symmetry in the bulk is now non-abelian at the boundary, as long as these charges are non-trivial.
I'm confused about something much more elementary you said earlier.
Okay.
When is it that the symmetry operator that acts on the region, under what conditions can it be written as products of operators at the two ends? Is this always the case, or?
Is not always the case. You need a gap, and you also need, of course, you need the symmetry to be unbroken, right? Like if you have a symmetry breaking ground state, then you can tell the difference by some local operator in the
But
middle
you
of
wrote
the
an
symmetry.
operator statement. But you wrote an operator statement. You wrote an operator statement.
It's not an op. Well, it's a statement. It's a state statement, right? It says
So
that
I cannot say that.
only applying to the ground state is this true.
I see.
It's not true for excited states.
Okay, because the operator statement is not true.
That's right.
Okay, thank you.
That's actually important to be careful about these arguments. Otherwise, you can derive many incorrect conclusions. Okay, so this projective symmetry action tells us, for one, it tells us that we have a degeneracy if we study the system on an interval, because all of these projective representations have some dimension greater than 1. So here's a very simple example that you can play with. Even if you don't like lattice models, I think you have to somehow love this example because it's so elegant. So when I write these operators, I'm going to write just capital X and capital Z for Pauli spin operators, sigma X, sigma Z. This is just shorthand. So the Hilbert space of this model is a tensor product. For each J, we have some two-state system, some spin 1/2 of these Paulis acting on it. And Hamiltonian is the sum of these terms, XZX, one for every site. The symmetries will be the product of the Z operators, but acting on the two sublattices of even and odd numbered sites. So we'll call the two symmetries Z2 even and Z2 odd, or E and O. Now the symmetry, so the Hamiltonian is what's called frustration free. All of the terms in the Hamiltonian commute with each other. So the ground state is just the mutual lowest eigenstate of all of these individual operators. And for these operators whose eigenvalue is plus or minus 1, it's just that the ground state is the one that is fixed by all of these operators. So what this means is, if we apply Z somewhere in the ground state, we can pull an XZX out of the ground state, and that cancels the Z's in the middle. And you can think about this, if you do it a bunch of times, what we've done, now canceling all the X squareds, what we've done is we've turned a product of Z's in a region into two X's at the ends. And now these X's, they show up on the other sublattice, right? You see we started with a Z, maybe here's like an even site, and we get an X on the odd site next to it at the end. So the endpoint operator, this should be E and O, the endpoint operator of E is charged under O and vice versa. So this is an example of Hamiltonian which has the non-trivial invariant that I mentioned. So to define a boundary condition of this model, just to check that
let
it
me
has,
make sure I understand this. So you're summing over J. J is both even and odd, or J is all integers?
in the Hamiltonian, J is all integers.
Okay.
But
so
but in these, so here J is also all integers. It's just that these are only going to be on the even sublattice, and these are only going to be on the odd sublattice.
I see. And you're using Z in both cases.
That's right. So
Okay.
so the trick here is that, you know, Z commutes with itself, so it's okay that there's one Z here, and otherwise we always have two X's that are on the same sublattice. So this Hamiltonian is symmetric.
Ryan, does this system have one boundary or two?
You mean, do we consider it on a half infinite line or on an interval?
Exactly.
So I'm about to consider it on an interval. That ends up being, I don't think it much, well, you have to be careful, of course, if you're going to study a half infinite system. It's always a little bit better to study it on an interval.
But then isn't there a difference between having an even and odd number of points?
Actually, no. They will be different boundary conditions. Well, sort of. It'll look different, but it'll really be the same.
Okay.
We'll end up with the same degeneracy in either case. So here is an example where I study it on an interval. Of course, there's many ways to end the system, but one very simple way is to just keep only the Hamiltonian terms that fit on the interval. And now these terms are small enough that we don't get some huge degeneracy by doing this. So let's say that the sites run from 0 to 2n. So it goes from an even site to an even site. If we project to the ground state of H, we can see what the symmetry operators do. So UE is going to be the product of all of the Z's. And I realize there's a typo here. So the thing in the middle shouldn't be there, or actually, let me think what happened here.
Looks correct.
Yeah, okay.
That's fine.
I agree, right? We're going to eliminate the Z's that are in the middle to write it this way. Okay, so I was second guessing my calculation for a second, but Ruben helped me. So, right. To see what the fate of the system is on an interval, we can project to the ground states. And if we look at what the operators become when we do that, they become this. And as claimed, you can see that they commute at the boundaries. Now, globally, of course, they commute because this is Z2 times Z2 symmetry. But we see that X2n anticommutes with Z2n and X0 anticommutes with Z0. And they're very far away from each other. So because the bulk is gapped, the two ends can't really talk to each other. So we can really think of it as a projective symmetry action on one and a projective symmetry action on the other for a total of a fourfold ground state degeneracy, 2 times 2. So there's another way to think about this that will be slightly more useful for us, which is to think about, instead of symmetry fractionalization, we think about an order parameter for these phases. And the way to come up with this order parameter is to take the expression that we had for symmetry fractionalization and just flip one side over so it becomes an expectation value. And so what we find is that if we take our symmetry operator in some region and then apply the conjugate of the adjoint of the endpoint operators to each end, we get an operator whose expectation value tends to a constant when these endpoints become very far away from each other. So we say that this operator is long-range ordered. Now, it's quite similar to saying that a 2-point correlation function of an order parameter goes to a non-zero value. But here it's not a local order parameter because of the symmetry string in between. So at a boundary, these do become local order parameters, which is that if you have a boundary from the SPT to the, if you have a boundary of the SPT, we can think of that as an interval from, or an interface from the SPT phase to the trivial phase. And the whole system here is symmetric because we're studying symmetry preserving boundary conditions. And so symmetry fractionalization will hold in this system where now the endpoint operator in the trivial phase will just be trivial. It'll be the identity. Whereas in the SPT phase, it'll be this non-trivially charged thing. And so the statement that the correlation function here goes to a constant, now this is an entire operator that has charge, right? Because its total charge just comes from this one endpoint rather than having two endpoints here that cancel each other. So we can think about this as now really just evaluating a 1-point function, which tells us that there's going to be some degeneracy at the edge. It's a bit like how we argue degeneracy in a spontaneous symmetry breaking system. So this acts like an order parameter where it's near the boundary. So the important reason to do this is that symmetry fractionalization is going to fail in our gapless systems. So this gives us a little bit less information about the boundary. We don't learn, for instance, it's a little bit more, it's a few more steps from here to think about there being a projective symmetry at the boundary. In gapless systems, we won't have that projective symmetry point of view, but we will have some kind of degeneracy. And the way to see that symmetry fractionalization fails is to just observe, just say, look at this example. Like here is the critical Ising chain. And if we apply the symmetry string in some region, of course, we know that that's how we define the disorder operator in this system. So the correlation function of this string goes to 0 as 1 over n to the quarter, where n is the number of sites here. And so there's no way to write this operator as a product of v0 and vn, because these have to be unitary, right? Still,
the system gapped or gapless now? This is a gapless system, right?
So now I'm telling you how symmetry fractionalization fails in gapless systems.
And I guess this is a variant of the question that Edward asked earlier. What does the degeneracy mean if the system is gapless?
So it can mean that, so we're always going to ask the question of degeneracy on an interval, like we did here. And there will always be, so there's some finite size splitting. So you don't have a continuum of states anymore. But what you can tell is how the finite size splitting scales with the length of the system. It always goes as 1 over L. So if you have ground states that, or excited states, you know, that go to 0 energy faster than 1 over L, we consider that a degeneracy.
I'm not sure that's completely convincing. I suspect that for non-free systems, it's possible to have states going to 0 faster than 1 over L that you wouldn't intuitively think of as reflecting boundary degeneracies.
That would be very interesting. I don't know any such examples, but I'd be happy to
hear. If you look harder, you'd find them. But
okay. Right. So let's talk about the very simplest example of gapless SPTs then. So as was suggested earlier, a maybe trivial thing that you can do is you can just take a gapless system and you can put an SPT on top. But there's still some interesting questions to ask here. So of course, if they're totally decoupled, then you have the edge modes from the SPT and you have whatever the boundary condition of the gapless system looks like. And you say, okay, well, it's non-trivial. But those are just the SPT edge modes. The really interesting question is when we start to couple these together, can the edge modes survive, right? And so to formulate this question, we're going to introduce, so we're going to have our global symmetry G, and it's going to be represented some way on the low energy degrees of freedom. And we're going to allow arbitrary couplings that preserve this global symmetry. So for instance,
sorry, Ryan, can you explain a little bit more on your notation? So G is the symmetry of the SPT. And what is G low energy? Is the symmetry of the low energy system after you couple the two systems, or?
Right, so the low energy degrees of freedom have some symmetry, and we're going to define the entire system as some, G is going to be the global symmetry that we preserve. It'll be the symmetry of the SPT. And G low, right, this is just how it's represented on the low energy degrees of freedom.
So G low is the symmetry of the CFT or of the...
That's right.
Okay.
That's right. So I do that basically so that I can talk about this very simple example where the gapless degrees of freedom are just the Ising chain. And here we have, the Ising chain only has a Z2 symmetry, right? But there's no Z2 SPT. So the best we can do here is we can have one of our Z2 symmetries act as the spin flip of the Ising chain, and the other one only act in the gap sector. And so here, the odd symmetry is the one that only acts in the gap sector. This is going to have a non-trivial string operator, which is the one we saw before. That will be long-range ordered, and that's enough to know that this system is going to have some boundary degeneracy. The other string operator is going to be the product of the gap string operator in the SPT and the disorder operator in the critical Ising chain. Right, so this will be one of these algebraically decaying string order parameters.
Sorry, I'm still confused about your answer to Xu Heng's question. So I think you answered him by saying G low is the global symmetry of the CFT, the blue, represented by the blue line.
Mm-hmm.
But doesn't, what symmetry is represented depend on how you couple the SPT, the gray line to the blue line? I mean, how are you coupling those two?
So we're picking the symmetry first, and then I'm going to say that you can couple them however you want, as long as we stay within this universality class.
Okay.
So defining the symmetries then defines the problem. I mean, you could, maybe if you have a Hamiltonian that you're already interested in, you would run the analysis a different way. You would see what symmetries there are, and then you would analyze them this way.
Ryan, are there two different kinds of Z's on this slide?
Yeah, so there's the Z's that are acting in the, so these are both spin 1/2 chains. The product of Z's up here is acting in the critical Ising chain, and here are acting in the cluster model that I showed you before.
Thank you.
You can combine these two. You can make it look less like a stack if you want, but really it's still going to be a stack. Okay, so the situation here is that only one of the string operators has long-range order, the other one has algebraic decay. So the question is, what happens with the boundary? And for people who like to think about CFTs, you could think about this model as having some discrete torsion. Now, discrete torsion just means that if we have some CFT, which is defined, which we're able to couple to a background gauge field. So here, A is a G gauge field. So rho of A is a G low gauge field. So there's some given way of coupling a CFT to a G low gauge field. We can modify that by any topological term for this background gauge field we like, and get a slightly different partition function. Now, in the case at hand, what we're using here for omega is the topological action from the cluster SPT. If we think about integrating out this gapped part, it's just going to give us this topological term. And normally we think about discrete torsion when we're actually going to orbifold this CFT. And that's true. If you're only studying local operators, then you can't see this. But since we're interested in these string operators, these actually do affect the charges of the string operators. As you can see, those come from computing, say, torus partition function with some symmetry twist around the spatial cycle and some symmetry twist around the temporal cycle. And if you set this up appropriately for the problem we have, that if you use this even string, right? So for the Z2 even that's acting on both of them, that we're going to be computing a particular twisted partition function whose first term, because it's an algebraically decaying string, its first term is not going to be a constant. It's going to be some, here Q is e to the minus beta over L. It's going to be some exponentially small term But the important part is there's going to be a minus sign in front, which is the charge. And that minus sign is just coming from this topological term. Okay, so how do we study the boundary in these kinds of systems? Well, I told you already that since there's one string operator that's long-range ordered and it's non-trivial charge, that becomes an order parameter at the boundary. And that implies some degeneracy. Well, but how much? We'll show that the degeneracy that you would expect from the gap system, which is fourfold on an interval, is actually reduced to twofold. And we can study this perturbatively. Basically, we can take we can do the same trick of integrating out the gapped system here, but when we do it with boundary, what we're going to be left with is a critical Ising chain and then some decoupled spin 1/2 at each end that comes from the SPT edge mode. And the fact that this was an SPT edge mode tells us that the symmetry action on it has to be projective. So the remaining symmetry operators, once we've projected into this space, are the usual just product of all the z's now. So here now there's only one z, right? So this is just some spin chain where the 0th spin is this extra spin. So one of our symmetries is going to be a product of z everywhere, and the other symmetry, which only acted in the SPT, and this is the only thing remaining of the SPT, only acts here, and it acts by Pauli x. So you can see that they don't commute with each other. Now, if you had another spin, there would be an x sub n here, so that globally the two symmetries would commute with each other. So in terms of CFT boundary conditions, the boundary conditions of the Ising chain is the free boundary condition, and you have two fixed boundary conditions. This looks like free plus free. So it's not really a Carty state because there's really two copies of the same boundary condition. So I'm going to write that as free plus free. And so the boundary entropy associated to this is just twice the boundary entropy of the free boundary condition, which is 1. So morally, this boundary entropy G equals 2 reflects the twofold degeneracy at the boundary of the SPT, and so the fourfold degeneracy on an interval. But this degeneracy is not stable. There's an operator that we can add that commutes with the symmetry, which is just XX, just the ferromagnetic coupling from this extra spin to the first spin of the critical Ising chain. And if we do that, we trigger a boundary flow from this free plus free boundary condition to the sum of the two fixed boundary conditions. And this...
Sorry, I'm kind of getting lost about what you're doing here. It's looking a little like the Kondo model. You're just coupling a spin 1/2 degree of freedom to the edge of an Ising model. Is that?
Yeah, you can totally think about this as like a kind of... It is a lot like the Kondo problem, although we're about to study an interval, which makes it a little bit different. But
yeah, but the point is you're just coupling a spin 1/2 degree of freedom to a CFT with some symmetry at the, and you're coupling the boundary. Is that right?
Yeah, it's like a Kondo problem, but with a funny symmetry action. The fact that we have this local symmetry here that came from the SPT. So the boundary entropy of each of these fixed boundary conditions is a 1/√2. And the boundary condition of the sum then is just √2. Now, this √2, it shows up in the degeneracy. That is, if we study this system on an interval, there are going to be 4 possibilities for how we fix the boundary conditions at the end. This is going to be plus plus, minus minus, plus minus, minus plus. But plus minus and minus plus, right? So the antisense boundary conditions are going to be lifted in energy from the boundary conditions where we choose the same one at the ends by an order 1/L energy, which is the same order as the other bulk states. So here we'd say, before coupling, these are all exponentially split, where the exponential is the correlation length of the gap sector. But now that we've added this XX, we've split that fourfold degeneracy into two. There's a 1 over L splitting between these. So that means that the
Did you
system.
tell us what the Hamiltonian is of the total system?
So this here is for all of the spins from so there's the first, let's say, we can think about it as a critical Ising chain. So it's the usual XX plus Z, except that Z is missing from the first site and the last site.
Okay, so you did tell us the Hamiltonian.
Yeah.
And this direct sum notation, these are like boundary states, like the usual way we describe boundary conditions by a boundary state in the closed sector. Is that how I should think of it, or do you mean something else?
So I don't mean anything too specific about the plus notation. I think if you think in terms of like modules, it really is morally like a direct sum of modules. But in terms of the Carty states,
modules for what algebra? The algebra of boundary operators or something?
yeah, insofar as you think about the boundary conditions as modules of the.
But modules have to be for an algebra. So the algebra is an algebra of boundary operators, or?
Right, for instance. But anyway, what you can think about it is it's a qubit that can, if it's in the up position or if it's in the plus position, then it's a fixed plus boundary condition. And the way you see that here is that if X has the eigenvalue +1, then it's like applying this polarizing field at the next site. But if it's minus, and that gives you the fixed plus, but if it's minus, then you get the opposite polarizing field at the first site, and that gives you fixed minus. So hopefully that helps, as I should have mentioned. That's how you kind of see that depending on the orientation of the spin, it's either fixed plus or fixed minus. So in that sense, it's like fixed plus plus fixed minus. So the total Hilbert space, if you like, there's the Hilbert space of where you have these boundary conditions, and this is the direct sum of all 4 of those Hilbert spaces. But now we put them all into one big Hilbert space, and we considered the energy splitting between them. Okay, so there's a twofold degeneracy in this system, which is interesting because there are 2 boundary conditions. It's a bit like the Majorana edge mode that we're familiar with in, say, the Kitaev chain, but that's a fermionic system. So I think it's quite interesting that we see Majorana-like physics in this gapless system, in this bosonic system, which we can get away with because it's gapless. So even in this trivial case, we're seeing something new. Okay, so.
Sorry, Ryan, about the last comment you made, is there some Jordan-Wigner transformation relating the two?
That's right. This is related by Jordan-Wigner transformation to it's a transition from, well, how do I want to say it?
You want me to quickly comment, or?
Oh yeah, go ahead. I'm trying to remember.
Yeah, so after Jordan-Wigner transformation, it's you can think of it as a phase transition between a single Kitaev chain and 2 Kitaev chains. And with the current model that Ryan is discussing, the Majorana edge modes would be exactly decoupled at the critical point, corresponding to the exact twofold degeneracy of the bottom 2 levels that Ryan has shown in this slide.
Okay. Thank you.
So
Okay.
I'm still confused about what the low-lying states look like. Can you summarize now which states are boundary states? What are low-lying states in the bulk associated with the fact that there will be in the end the gapless modes and so forth?
So the bulk is non-degenerate. The first excited state has energy 1 over L if you study the system on a circle. So here we're identifying boundary states by degeneracy on an interval. And degeneracy means that the energy splitting is faster than 1 over L. So here we have 2 states, at very low energies that are, there's some exponentially small mixing between these.
So you have two states. So the ground state is twofold degenerate,
Yeah.
or nearly twofold degenerate.
Mm-hmm.
Sorry, twofold nearly degenerate.
Yes.
And then there are states at order 1 over L.
That's right.
And you interpret in the two states, are they exactly degenerate, or is it exponentially in L? What's the energy difference?
Yeah, so they're going to be exponentially split in general, given by the correlation length of the gapped part of the system. So, right. Let me briefly describe why this is stable. So if we were to add just a Z at the end, then we would end up with just the critical Ising chain on the entire system. And that wouldn't have any edge modes. That would just be the free boundary condition again. But of course, this Z is forbidden by our symmetry, right? One of our symmetries is just X at that first spin. And in terms of the CFT, this operator that we'd like to add, Z0, it's a boundary condition changing operator. It's really a sum of the two boundary condition changing operators from plus to minus and minus to plus. There's only one primary in this case, and this is a sum of the two primaries. Now, the discrete torsion affects the charge of this BCC operator. So we can actually see this from the partition function point of view, but something that's a bit disappointing about it is that even though we had this non-trivially charged string operators, it ends up that where the real magic happens that gives us the edge mode, right, or at least the stability, we really have to study the charges of these boundary operators instead. So there's a question here of when do the bulk invariants of these string operators relate to the charges of these BCC operators? Now, of course, in this case, the boundary operator, the single Z, you can think of it as it's actually coming from the bulk disorder operator if we have a whole bunch of Z's here, right? And we've just shortened it so that it acts as the boundary. So there's some fusion of the bulk string to the boundary, but it's not clear from this example whether it's enough to just know about those bulk string operator charges to know that this boundary mode is there. So here's a quick summary of that example. The questions that we want to ask now are, what is the bulk boundary correspondence? Like, how could we have seen this that this edge mode is there, especially in more general systems? Like in particular, we're interested in gapless SPTs where none of the symmetries are gapped. Or we might even be interested in gapless SPTs which are not of this stacked form. So let's see. I'm running out of time. I'm just going to quickly tell you an example of a critical point that looks like it might be non-trivial, but actually has trivial edges. But let me actually not talk about that. And instead, I'll talk about this example that we're working out with Saran Brahmbabu, which is that now if we consider this symmetry class Z3 times Z3, there are 3 SPTs corresponding to this cohomology group. And there's a nice phase diagram that includes all of them, where we have some triple point, and we have trivial phase, one of the SPTs, and one of the other SPTs. Now, it turns out that there's some Z3 symmetry that rotates these phase, that rotates this phase diagram, but it's not local with respect to the Z3 times Z3 global symmetry. And we find that only this transition from one SPT to the other has edge modes, whereas the trivial transition to the either SPT or SPT prime both have trivial boundary conditions. So this is an interesting example. If we think about the string operators for the symmetries, so all of the symmetries are gapped now. So at the transition, there's Z3 times Z3 is represented faithfully in the CFD. So all of the string operators are algebraic. So at best, we can look at the string operators which decay the slowest by the slowest power of the length. And it turns out that we're always going to have a degeneracy at these kinds of SPT transitions, where there's going to be the string order parameter here and the string order parameter here that has a different charge, and they're going to become degenerate. They're going to both be algebraic here, so they're going from being ordered to disordered in both cases. It happens symmetrically at the transition. So along this line, for instance, there's a twofold degeneracy among all of the string operators. There's a string operator of trivial charge, and then there's a string operator of non-trivial charge. So only in the transition where both of those lightest string operators have non-trivial charges are there edge modes. So there's some indication here that if enough of the string operators have non-trivial charges, that we're going to have edge modes.
Excuse me.
Yes.
Sorry, Ryan, just make sure. You are saying these are the transition between two different SPT, but gapless SPT, right? The green line?
So these here, these are SPTs, just ordinary gapped SPTs in these open regions. You can think about this triple point here as a kind of transition between gapless SPTs. I mean, here, it's hard to phrase exactly what this would be, but both of these lines are more or less the same CFT. They just differ by some discrete torsion, right? So here, the discrete torsion is changing. We think this is like SE3 level 1. And so you can kind of think about that as a gapless SPT transition. Does that answer your question?
So the phase indeed are gapped in the bulk part, while only the transition are gapless. And there's also a tri-intersecting point.
Mm-hmm.
But your earlier comment about the transition between SPT to trivial and SPT prime to trivial, those transitions are still there in gapless, correct?
Mm-hmm. That's right.
Okay.
But these ones don't have edge modes.
Okay, no problem. I misheard something. Okay.
Mm-hmm. So there's some cute argument I won't go into to why the edge modes are there, but I want to pose this conjecture, which is that if the system doesn't have a nearby trivial phase, that it has to have non-trivial boundary conditions. So that's true in this Z3 times Z3 example. The only system, the only phase here, which is not next to the trivial phase, is also the only one that has edge modes. So likewise, if you study a transition between the cluster SPT and the trivial SPT, that this was the Ising times cluster model that we studied, and it has edge modes. And so this should not be colored. This doesn't have edge modes. So the edge modes would be here, and then these would just be ordinary Ising models with no edge modes. I think it's an interesting conjecture. Can prove one direction of it. Is there a question?
I'm sorry, but the title in earlier slide, you say gapless SPT, but without gap symmetry subgroup. That's the previous slide. So when you say gapless SPT, you mean just along the transition as gapless SPT?
Yeah, so I'm not very concerned with whether these are stable phases or not. You can always add more symmetries that prevent the relevant operators from turning on. It's not necessary to have those symmetries to explain the edge modes. So I'm not so interested in them.
If you didn't have the matter, you just had the gauge field of the Z3 times Z3, would you get the same effect in the gap system?
What do you mean by the same effect?
Well, you gave an example of an overfold with or without discrete torsion or with different discrete torsion. And I guess that the group of the overfold was Z3 times Z3.
Yes.
Which means that the way I interpret this is that you have a CFT with a Z3 times Z3 global symmetry. And then you gauge this symmetry with or without discrete torsion.
Mm-hmm.
So we can do the same thing without the gauge, without the matter system, just without the CFT. Will we get the same effect? Because if so, then the CFT doesn't play a role here.
No, so if you just study the gap system, then the two SPTs have the edge modes and the trivial phase doesn't.
Imagine I just study a Z3 times Z3 gauge with or without, with various discrete torsion. Will I get the same effects or not? I'm trying to see whether the effect really comes only from, whether it comes only from the gauging or it has something to do with the CFT before gauging.
It's a different effect. I really think that, you know, if you have a group Z3 and you think about, you would normally say that, okay, there's three elements. There's a trivial phase and two non-trivial phases, which are conjugate. But here what we have are more or less two trivial phases that are conjugate to each other and one non-trivial phase. So in a sense, this transition here is the easiest one to describe. We don't actually need any discrete torsion to describe this. It's like two copies of the three-state Potts model where you gauge the diagonal Z3 symmetry. And then these are given by that, but then you add some discrete torsion for the remaining Z3 times Z3. So yeah, these things don't form a group. And here we're seeing a feature of that there's no group law here. I'm not sure if that answers your question, but maybe we can talk about it more later.
I was just trying to understand whether you could have the same effect without the CFT in a gap system, which is a gauge theory, a discrete gauge theory.
I guess, so discrete gauge theories in one dimension, though, are 1 + 1 dimension, are not very interesting. They're all symmetry breaking for the dual magnetic symmetries. So there we know everything that happens.
But Ryan, I have a variant of Nati's question. So what if you replace the three-state Potts by any other CFT with a Z3 symmetry? Do you get a different qualitative result?
Well, the conjecture is that if you don't have the trivial, if the trivial phase is not accessible by some relevant perturbation, then you have boundary conditions. Otherwise, yeah, that's the main point that I want to make by this phase diagram. Of course, a general CFT with Z3 times Z3 symmetry has a phase diagram that may look nothing like this.
Okay, thank you.
Okay.
Ryan, sorry, I'm confused by something basic. Just this phases. You study 1 + 1D phases, and they are gapped SPT, three kinds and one trivial kind. You are studying the transition between them and also looking at the boundary or the edge modes. The claim you have is say on the bottom, you say the top line has edge modes in the 0 + 1D, and the transition is still 1 + 1D gapless, correct, right?
Mm-hmm.
And now the thing is that I'm puzzled by why only, maybe you explain, but why only SPT to SPT prime has this edge modes? I suppose you study those degeneracy with, you know, even finer exponential decay degeneracy compared to this 1/L polynomial degeneracy. But why only?
So along these lines, the degeneracy is completely lifted. right? There's a unique ground state, and then it's 1 over L to the first excited state on an interval. Whereas here, there's 3 exponentially close ground states, and then 1 over L to the first excited state. Now, I didn't tell you why that is, but
is there some mathematical thing you can say about the representation or something? More like different? Why is that different from the class 1 and class 2 SPT compared to with 0 versus 2 and 0 versus 1?
Yeah, it's a good question. I mean, it's unclear what the mathematical structure is in these kinds of systems because we don't have this projective symmetry interpretation. Actually, I misspoke earlier. So here, because all of the symmetries are gapless, there's no gap, right? There's no correlation length in any sector along this line. So actually what you have is you have 3 ground states that are algebraically split, but at a power more than 1 over L. It's like 1 over L to the 5/3 or something. And then you have 1 over L to the first excited state. So here it's a faster than 1 over L algebraic degeneracy. That was a technical point. Anyway, so the question of a bulk boundary correspondence is very interesting. You'd like to have some kind of like mathematical way maybe of thinking about the charges of all these string operators and saying that if they have such and such values, then we have to have edge modes. But I think maybe the best we're going to be able to do is we're going to say that if there's no trivial phase nearby, then we have to have edge modes. And then we can start to wonder, okay, maybe if there's a trivial phase nearby, that's a phase where a trivially charged string operator is becoming long range ordered. Maybe we expect that operator to have small dimension at the critical point. I'm not really sure. I think it's an interesting question. But there's one direction of this argument that I can hand wave, which is at least to say that if you can flow to the trivial phase, then you have a trivial boundary condition. And this more or less follows from the G theorem. If you consider periodic boundary conditions in the context of the G theorem, it has a boundary entropy of 1. And if you perform the perturbation in some region along the circle, that in that region, you're going to flow to the trivial phase, and you're going to end up creating 2 interfaces to the trivial phase. In other words, 2 boundary conditions. And so by the G theorem, these boundary conditions have to have G less than 1. And that implies, although I didn't argue it for you, that there are no edge modes. But the other direction is very mysterious. I guess you'd want to argue that somehow all Carty states of G less than 1 are associated with nearby gapped phases, right? So yeah, I'm not sure how to do that, but I think it's a very cool type of question. So I was going to tell you about these intrinsically gapless SPTs, but maybe I can tell you in the meeting afterwards. So just quickly summarize. The gapless SPTs are gapless systems with symmetry protected edge modes. Okay, so maybe there can be some question about what these edge modes are, but I think that if you study it in terms of finite size splitting on an interval, that it's a sensible question. We can construct these in a sort of trivial way by taking gapless systems and putting SPTs on top, but still the question of whether there are stable edge modes in those cases are quite interesting, and I think the general story is not resolved. If part of the protecting symmetry is gapped, meaning that we have a non-trivial string operator which is long-range ordered, then it's easy to argue the edge modes because it becomes an order parameter at the boundary. So the boundary has some kind of symmetry breaking type degeneracy, or at least it has an order parameter. There are also intrinsically gapless SPTs that I didn't tell you about. But anyway, so the questions are, what is the correct bulk boundary correspondence for gapless SPTs? For instance, do the lightest boundary condition changing operators come from the lightest bulk string operators or disorder operators? Do all trivial boundary conditions, trivial meaning just that they have small boundary entropy, arise from perturbing into a nearby bulk phase by some relevant operator? Maybe more generally, you can ask that non-trivial boundary conditions perhaps always occur when you tune the system through a phase transition, something like that, right? You tune it against the RG flow. So are there intrinsically gapless SPTs without any gap sector at all? So in the intrinsically gapless SPTs we know so far, there's some emergent anomaly which requires there to be a gap sector where part of the charges are acting. And once we've included these in the story, we've sort of exhausted the use of our topological terms, and we have to start to think about CFTs which have non-trivial charges for the light twist operators. So for instance, if you have a Z2 symmetric CFT, something like Ising, in the twisted sector, there are three primaries. There's the disorder operator, which is the lightest primary, and that's neutral under Z2. But then there's two charged primaries above that. And you can wonder if maybe if it's ever reversed, if there are any CFTs where the lightest Z2 twist operator is actually odd. And that would be interesting in a bosonic system because it's not something that you can arrange by turning on some discrete torsion. And of course, I told you about 1 + 1D, but I can't help but mention that we have some numerical evidence of edge modes in higher dimensions, and we're very interested in understanding the boundary physics of those. So thank you very much.
Thank you, Ryan, for a beautiful talk. Are there any questions?
I have more of a comment than a question about the fourth bullet point here. Mm-hmm. So first of all, right, this is a clarification that the Z2 has to be non-anomalous for the question to make sense.
That's right. Yeah,
I think you assumed at the very beginning of the talk. And the second comment I have is that this question is equivalent. So a twist operator, a Z2 twist operator, its Z2 charge is determined by its Lorentz spin. So the question can be equivalently phrased as, is the lightest Z2 twist operators, does it always have an integer spin rather than half integer?
Right, yeah.
Yeah, I'm not sure if this helps answering the question, but it's just a reformulation of the question.
I was hoping maybe like the bootstrap could have something to say about this question.
Yeah, I actually thought about the exact same question when I was doing the Z2 bootstrap. I don't remember if I came to a conclusion, but I did think about it before.
Mm-hmm. I'd be happy to talk about it more.
Okay.
So I have a question. So I'm trying to understand your statement that we can think of discrete torsion as coupling an SPT phase to a critical model, like a criticalizing model, and how general that is. And so it seems to me that if I have a conformal field theory with a G symmetry, then I can, in principle, quote, add discrete torsion. But that's just coupling the theory to an invertible topological theory. Mm-hmm. Is it just, is this stacking of yours just the statement that I'm coupling a conformal field theory to an invertible theory?
Yeah, I think it's exactly the same. I mean, stacking and tensor product are the same. And this invertible TQFT is just the infrared limit of this SPT phase.
Okay, well, I don't know. To me, this statement looks pretty mysterious when you said you're stacking these systems. I think you're just interpreting the discrete torsion, which is a term in the action, as an invertible topological theory and saying I'm coupling to an SPT phase that way.
That's fine. I mean, we do study systems from lattice Hamiltonians, right? This work involves a lot of the numerical checking of the degenerate.
Well, I'm curious
like
to know.
Greg, I'm sorry, I don't understand your question. The discrete torsion is a term for dynamical gauge fields, not for classical gauge fields. The term in the action in the invertible theory is for classical fields.
No. I mean, we could add background gauge fields for the G symmetry.
Right. I'm only using background gauge fields in this talk, and maybe.
Yeah, I mean, Nadi, if we actually do the orbifold and sum over the twisted sectors, then yeah, we're making those G gauge fields dynamical, but we don't
I thought that this is what he was doing.
Then I'm lost.
No. So all the G is always a global symmetry here. You can think about what happens to.
But you said you have an orbifold. Didn't you say you have a Z3 times Z3 orbifold?
That's yes, but that's not an orbifold by the global symmetry. That just happens to be what this CFT is.
Oh, so
I'm sorry if that was confusing.
Okay, now I'm totally lost. I thought I understood this. Like, is G a global symmetry of the system after orbifolding?
After orbifolding, that's right. Part of G involves the magnetic symmetry of the orbifold.
Okay.
So it's probably like the quantum symmetry.
Yeah, the quantum symmetry.
Yeah.
Uh-huh. Right.
Brian, oh, sorry. Brian, can you go back to your last slide? So I think actually I have a counterexample to your fourth bullet point.
Oh, good.
Yeah, so consider the monster CFT. It's a holomorphic CFT, one of my favorite CFT. And I think if you take Z2 to be one of the Z2 subgroup of the monster group, to be more explicit, is the 2A subgroup of the monster group, then its leading Z2 twist operator is Z2 odd.
Interesting.
In fact, that's the module that people use to construct the baby monster VOA, super VOA. Very
cool. So now the question would be to study the boundaries of that system and ask maybe it's a gapless SPT.
Yeah. You can see this directly from the Mackay-Townsend series of 2A.
Right, you mean just by studying with the S transformation.
That's right. Yeah, the S transformation of the Mackay-Townsend series. That's right.
Sorry, the T transformation, right?
Sorry, is it?
S then T.
Yeah, maybe there's a T too. Yeah.
Well, you just have to look at the spin, so it's enough to just see.
That's right. Yeah. So you just have to see the. Well, yeah. Well, the charge is determined by the spin, so you don't necessarily have to do the T, but yes.
But right, if you know the action of Z2 on local operators, you just do S to figure out what the twist operator spectrum is.
Exactly.
So I have a comment related to this comment. On slide 28, you started to show the partition function for T2 with these extra coefficients. Is this a mock modular form? Yes, but right at the end.
So this what I was just discussing the Ising. So what you'll end up with is something which won't be holomorphic in general. So here I wrote it where just Q is real, e to the minus beta over H. But in general, this has Q and Q bar. So it's not holomorphic. It's these partition functions, they're modular or equivariant. So for, there's an action of SL2Z on the decorated tori, and you have a partition function for each one that this SL2Z has to act nicely on. I suppose that when you're going to study this question for the monster group, you get some interesting modular forms, but right, because it could be holomorphic, right?
Well, you get mock modular forms which are meromorphic in general. So So it would be nice. Well, do you know the other coefficients of this series? Just one can easily figure out if it's some known modular form.
The one I was starting to write here is just comes from the Ising CFT. So this is some theta function, the square root of a theta function.
Okay, there you go. Well,
maybe with some dedicant ages. What's that?
So there are a lot of lattice VOAs where the partition function turns out to be the theta function. So it might be related to that, but do you know which theta function exactly, or can you say more?
Well, this is a C equals half the CFT. So the conformal blocks you can look up. They're like the standard Jacobi theta functions with some ratios of them.
Okay, cool.
But yeah, this series is completely known. I think that the partition functions of all the models that I've talked about are very simple to compute. They won't be that interesting from like a perspective, like a number theory point of view, for instance. But because we're more interested in the signs that show up, or maybe what these fractions are.
I wonder if you could restate the main point you're making just for a CFT person. I mean, so we understand as CFT, we understand discrete torsion, we understand how you can break, add boundary terms. So what is, how would you interpret this this slide here, the one you're showing, or this phase diagram, just purely in terms of CFT with maybe some boundary interactions?
Yeah, I think it's hard to say. I mean,
because SPT, I'm just going to read that. For that, I'm just going to read the discrete torsion for background G gauge fields.
Right. So the question is really about boundary conditions, right? So we want to say that in such and such a situation that we have non-trivial boundary conditions.
Okay, but I mean, people have studied at length, the Carty conditions and written down the boundary states and all that in the presence of discrete torsion. But maybe they didn't ask a question you're asking, but I'm not quite sure what the question is that you're asking.
So I'm not sure if people actually did study the boundary conditions with discrete torsion, or at least they weren't interested in degeneracy if they did. So maybe people saw this fixed plus fixed minus boundary condition before, but yeah, I don't know any references about it. I know some paper by Watts that just kind of says that here are some more boundary conditions, but the stability is really the point. The fact that the BCC operator that would flow from these like interesting G greater than 1 boundary conditions to a more mundane, say, free boundary condition, that those BCC operators are charged because of the discrete torsion.
Okay.
So
but that can presumably also be stated in a CFT language, right? It's probably related to the existence of some relevant operator on the boundary that triggered.
Yeah,
absolutely.
Yeah, I think so.
So, right. So here, this operator, these BCC operators show up in if you think about state operator correspondence, they are associated with these Hilbert spaces on the interval where you choose boundary conditions for one boundary condition on one side and the other boundary condition on the other. So you can think of that's forcing a domain wall here, right? So or a symmetry defect, if you like, so that when we apply the symmetry in the other direction, which is now going to mix up this plus and minus, right? So that's why we have to start taking sums that we're going to get a minus sign from that. You have to combine this with hermiticity to make sure that you always want to combine them with a plus rather than a minus as well. But in general, you wonder, yeah, it's hard to say. It's hard to even enumerate all of the boundary conditions in an interesting CFT. Maybe in a minimal model it's very easy, but in general.
Do you have an example with a minimal model?
So of course there's this Ising example, but you want something different?
Well, we understand all the possible boundary conditions in Ising.
Right. Yeah, so here it's very easy. I mean, there's only 3 players, the 2 fixed boundary conditions and the free boundary condition. And then we just have to combine them in different ways. And so it's when you start with this perturbative point of view, it's quite nice, where you initially have the decoupled edge mode of the SPT. So you have some of free boundary conditions, but you have a weird symmetry action on the disorder operator, or on the, yeah, you have some weird symmetry action on the vector space of these boundary conditions. So presumably,
can I just make a quick comment?
Yes.
Just on Nati's comment that we understand all the boundary conditions of the Ising CFT, and of course, in a way that's true, right? We know there's a free or fixed boundary condition, but you could also argue that in a way, the boundary condition that Ryan is talking about was in essence missed, right? Like this direct sum of these 2 boundary conditions. It's maybe not a Cardy state boundary condition, but it's a valid boundary condition under imposing certain symmetries on your system. And
it's not local.
That broader question.
I thought the condition is that the boundary condition should be local, and then there are only 3 of them.
It is local. It's just that you need to add an extra spin.
But then you're changing the model. That was my comment about the condo-like aspect of this.
Yes. But yeah, the game is exactly as in solving the condo problems. You're just looking for the most relevant couplings here. And we're finding that when you have this projective symmetry action, that you'll never be able to go all the way to get G less than 1, or to get G equals 1. That there will always be some place where you have to stop. So here it's that you can't add the disorder operator that's going to give you the flow from the sum of the 2 fixed boundary conditions to the free boundary condition. So you can't add this Z at the end.
Right. Maybe another way of thinking about it is that we're supplementing the Ising CFT with more symmetries than it usually has in a way, right? Usually you might say Ising CFT as an on-site symmetry might be Z2, right? But now we're supplementing with an extra Z2, right? That's what you're doing. And then you get these more exotic boundary conditions.
But that's not totally necessary, right? Like this Z3 times Z3 example, really these are all global symmetries of the CFT. Right? This of the G acts faithfully. So, but we're doing something by including discrete torsion in the study of the boundary conditions.
Ryan, excuse me. I'm still confused to interpret the result exactly on this slide. So you have 3 phases, trivial, say zeros, and let's say k null k equals 0, and SPT1, SPT prime, SPT2. If I stack the whole phases by SPT1, just one layer for the whole system, so I suppose I will shift the SPT class, so you will rotate the phase diagram by 120 degrees, right?
That's right.
So now I want to check the consistency of this phase diagram. That means that the result should also switch the critical line that you draw in green with this additional edge modes, even though the system on the critical line is already gapless, but there's additional degeneracy. So you are saying there's something special about degeneracy.
Yeah, so when you stack the SPT on top, then say here, now you're going to have 9 states. Or sorry, you're going to have the SPT edge mode there as well as the edge mode that you already have. And now there will be a way of coupling them together that it just becomes trivial Whereas here, now this green line will move over here. Whereas here at the boundary, you won't be able to completely get rid of the SPT edge mode. You'll be able to take it from g equals 3 to g equals square root 3, but you won't be able to get rid of it.
So the main point here is that once you stack additional SPT, you are able to use the SPT edge modes to couple to the degeneracy from gapless CFT, and then certain edge modes will be somehow still robust, but others will not be. And there's only one transition between two of the SPT, those degeneracies still somehow robust.
Yeah, every time you add the SPT, we're just going to allow any coupling that obeys the symmetry. Sorry for the airplane. It'll be over in a second. Right.
Is there some general statement you can make about this other than just this system? Other SPT phases, say getting any Zn costs, and then you draw those phase diagram. What will be a spatial transition between two SPT? I think here is one example.
This example generalizes to Zn times Zn. The most general thing I can say is just about the nearby gapped phases. Now, maybe you'd like to say that if enough of the if enough of the light string operators are charged, then we also have to have edge modes. But I don't know how to prove something like that. Right? You want to relate the BCC operators to the bulk operators. Seems like maybe someone who's very good at thinking about these series can form some kind of bound that you need. But yeah, I'm interested in checking out this monster example.
Oh, God.
Thank you. I'll ask you later. Thank you.
Yeah, I'd be happy to talk more about it.